Welcome everyone for today's 10th live interaction session. So first let me share my screen. Sorry. Here. Okay. So welcome all of you for today's 10th live interaction session on MATLAB based programming lab in chemical engineering. This is an NPTEL course taught by Professor Parag Deshpande. I will just give my short introduction. So I have completed my BTech in chemical engineering from SVNIT Surat in 2019. After that I did 1 year job at Reliance Industries Limited at Jamnagar. There I learned how to use SPN Plus software for various industrial problems. Then I completed my masters from IIT Kharagpur in 2022. There I learned a similar course to this MATLAB course from Professor Parag Deshpande. Currently, I am pursuing my PhD from IIT Bombay. So this is my web page and LinkedIn ID, and this is the YouTube link where all the videos of live interaction sessions are getting uploaded. So before starting today's session, let's first discuss what we saw in the last week. So last week we discussed about boundary value problems and we learned how we can use BVP4C inbuilt function for solving boundary value problems. Further, we started or we I gave a small introduction on partial differential equations, and we started looking at some previous year assignment questions. So we'll just follow this. Let's start today's session. So we will start with this question of various kinds of partial differential equations like elliptic, parabolic, and hyperbolic. This we have already discussed in the last class, but I will again go through it. Just give me a minute. I will open my notes. So I will open my notes. So we have already learned about various kinds of partial differential equations. So I will just go through it once again. So this is the differential equation where we can write it as this is a second order differential equation where summation I equal to 1 to 3, summation j equal to 1 to 3 aij del square u by del xi del xj is equal to r. This is the kind of differential equation, and when we open it up, all our coefficients a11, a12, a13, a21, a22, a23, and a31, a32, a33 are there. And when we construct the matrix of these coefficients where a11 is coefficient of del square u by del x1 square, a12 is coefficient of del square u by del x1 del x2, and a13 is coefficient of del square u by del x1 del x3. Similarly, a21 is coefficient of del 2 u by del x2 del x1. A22 is coefficient of del 2 u by del x2 and del x2 square, I'm sorry, and A23 is coefficient of del 2 u by del x2 del x3. Similarly, A31 is the coefficient of del 2 u by del x3 del x1. A32 is coefficient of del 2 u by del x3 del x2, and A33 is coefficient of del 2 u by del x3 square. And we form this matrix, coefficient matrix, and when we find the eigenvalues of this matrix, if we get all eigenvalues as positive eigenvalues, then all eigenvalues as either positive or either negative, meaning the same sign. If let's say I'm getting three eigenvalues and if three of them are positive, then it is hyperbolic PD. Or let's say if I'm getting three eigenvalues and I'm getting all three negative, then the basic word is all eigenvalues are of same sign. Then this kind of partial differential equation is called hyperbolic partial differential equation. Then there is another type, that is elliptic PD. Elliptic PD is there when all the eigenvalues are either of I'm sorry. Elliptic is where all the eigenvalues are either positive or negative. Hyperbolic is where some are positive and some are negative. That is called hyperbolic PD. And parabolic is called when there is at least one zero in PD. So we have three types of partial differential equation. We need to remember this criteria. Elliptic is called when all eigenvalues are either positive or negative. Hyperbolic is called when there are some positive, some negative. and parabolic is called when there is at least one zero. So let's try to look at this problem. We have the statement of we have to find which kind of PD is this. So our equation is del 2u by del x square plus del 2u by del y square plus del 2u by del z square is equal to 0. So if we form this coefficient matrix, so we have only this coefficient del 2u by del x1 square, del 2u by del x2 square and del 2u by del x3 square. So if we put these three coefficient, so it matrix will be 1 0 0 0 1 0 0 0 1. And if we find the eigenvalues, let's try to find the eigenvalues using MATLAB. This part is already taught in earlier lectures where we know how to find the eigenvalues. So wait, yeah. So our equation was this was our eigenvalue matrix 1 0 0 0 1 0 and 0 0 1. So let's put it there in MATLAB and see what are the eigenvalues that we are obtaining. Okay, so just give me a minute. I will just open one live script. Yeah, so let's say my equation from here was, okay, I don't need to do it here. I can just do it in command window is equal to 1 0 0 0 1 0 and 0 0 1. And let's say if I'm finding the eigenvalues, so I will put eigen eig command or eig MATLAB inbuilt that function. So eig of a will give me eigenvalues. So I'm getting my eigenvalues as 1, 1, 1. So all three are of positive signs or of same signs. So that's why this is called elliptic PD. So let's say this equation. So here del u by del t is equal to del 2u by del x square plus del 2u by del y square. So here we can see that we have coefficients of only x and y in this second order, but no second order coefficient of del u by del t. So that term will be 0. So our equation, our this coefficient matrix will be, for this term it is 1, for this term it is 1, and here there is no coefficient of del 2u by del t square. So this term will be, all will be 0. So our matrix will be 1 0 0 0 1 0 0 0 0. So let's try to find out using here. So 1 0 0 0 1 0 and 0 0 0. So eigenvalues are 0 1 1. So we are getting at least 1 0. So this type of equation is called parabolic partial differential equation. And here this thing del 2 u by del t square. So now here there is del square u by del t square is equal to del square u by del x square plus del square u by del y square. So now this term, if I go this side, so it is del square u by del x square plus del square u by del y square minus del square u by del t square. So there is at least one. Okay, so here instead of 1 there is minus 1. So if I try to find it, so it is 1 negative and 2 positive. So it is the combination of positive and negative. So it is called hyperbolic partial differential equations. Okay. So there is another way also to compute it by, if we are having this del square u by del x square plus 2 times b del square u by del x del y plus c times del square u by del y square. I'm having this kind of term, then I can find b square minus ac. And if my b square minus ac is greater than 0, it is hyperbolic. It is equal to 0, then it is parabolic, and it is less than 0, then it is elliptic PD. Okay. So this is the theory. So what is easy way to remember when you are having Laplace kind of equation? This is Laplace equation, right? Del square u by del x square plus del square u by del y square plus del square u by del z square. This is Laplace equation. So when there is a Laplace equation, it is always elliptic. Then okay, this equation is not Laplace, but what is there? There is one del square u by del t square on the one hand of equal to sign. So on left hand side there is one del square u by del x square, and on other side let's say we are having del square u by del y square and del square u by del z square. So this type of equation are hyperbolic, and let's say we are having one term that is not of second order. See this del u by del t, this is first order and another two are second order. So this type of equation are called parabolic partial differential equation. Okay, so let's try to solve this problem. So we are supposed to say, so this is the this is Laplace equation, right? Del square d by del x square plus del square d by del y square is equal to 0. And we already looked at when there is a Laplace equation. So Laplace equation is of kind elliptic partial differential equation. So for one, it is uh, for A is related to 1. So 1A, so option is either A, C or D. Now this equation. So this is kind of del square u by del t square is equal to del square u by del x square plus this. So we are having eigenvalues of 1, 0 and 0 minus 1. So when we solve this, we get equation of parabolic where there is eigenvalue of eigenvalues of at least 1. Sorry, not parabolic, hyperbolic, where eigenvalue 1, eigenvalue is 0. Let's see. For C, this part, coefficient of this term is 1, and I'm taking it 1 because it is something's square. So that is always going to be positive. So let's say I'm taking it 1. So this coefficient is 1 and this coefficient is minus 1. So I do 1, 0 and 0 minus 1. Okay, and let's say if I'm finding eigenvalues, so I'm getting one positive and one negative. So when there is a mixture of positive and negative, it is called hyperbolic PD. So this B is related to 3 hyperbolic PD. I hope this question is clear to everyone. Let's move ahead with the next problem. The inbuilt MATLAB solver pdepe solves only parabolic one-dimensional partial differential equations. Okay, let's try to search about what is this pdepe MATLAB inbuilt solver. pdepe. Okay, so let's search it and see what we are getting. So see what is the description saying? Solve one-dimensional parabolic and elliptic PDEs. So what is the statement? Statement says that the inbuilt MATLAB solver PDP solves only parabolic. So that is wrong. It solves both elliptic as well as parabolic partial differential equation. You can see it from here. So this sentence is not correct. So this is the false statement. Okay, let's take next problem. Consider the following partial differential equation as given by Fick's law of diffusion, that is given by del C by del T is equal to D del square C by del X square. So first statement is the order of partial differential equation is 2. Is this correct or not? Yes, this is second order PD because this term is del square C by del X square. So this is second order PD. So this statement is correct. The second statement is saying that this is parabolic PD. So for parabolic PD, we have two term, two variables T and X, and only one term is first order and another is second. Another is no first order term. Another is no second order term. So this coefficient is D and we know that diffusivity is always positive. So let's say this coefficient is 1. So 1, 0 and for this term 0, 0. So let's say I'm trying to find what do you say eigenvalue. So when it is 1, 0 and 0, 0, what do we get? Eigenvalues as 0 and 1. So there is at least one 0 present in our solution. So when there is at least one 0 present in our system, when there is at least one 0 present in our eigenvalues, so it is called parabolic PD. And what is told, this is a parabolic PD. So both statements are correct. Okay. So the correct answer will be C. Both the statements 1 and 2 are correct. Okay. So you can also remember from here, see, this is analogous equation. So del C by del T is equal to del 2 u by del x square. This is same kind of equation. So this will always be parabolic. You don't need to calculate eigenvalues and those stuffs every time. So you can directly remember this. So this is both statements are correct where order of partial differential equation is 2 and this is a parabolic partial differential equation. Okay, let's move it. Okay, let's take this problem after some time. This problem also. Let's first finish this theoretical question and then go to PD function. Okay. If a problem governed by a PDE belongs to the spherical symmetry, then the value of M for the solution by PDE solver in MATLAB is what? Okay. So here, if we see the syntax of PDE solver, so solution is equal to PDE, that is MATLAB inbuilt function that says M, comma PDE function. So equation that we will be writing. IC func means initial condition function, then boundary condition function, then values of x mass and t span. So what is this m here? So let's try to figure out what is this m. So wait, let me. Okay, the scalar m represents the symmetry of the problem. Is it its slab, cylindrical or spherical? Okay, about m it is given below. When m is equal to 0, it represents uh, Cartesian coordinates. When m is equal to 1, it represents cylindrical coordinates. And when m is equal to 2, it represents this spherical coordinates. It is written somewhere here. So I'm just trying to find that. Yeah, here. When m is equal to value of m, that is symmetry constant. This symmetry constant specified as one of the values in this table. So m specifies the type of problem in the equations specified by the PDE function. Once you rewrite the equations in the form expected by PDP, you can read the value of m from the equation. So when m is equal to 0, it is one-dimensional Cartesian coordinates with no symmetry. Then when m is equal to 1, it is two-dimensional cylindrical coordinates. Okay, and when m is equal to 3, it is three-dimensional spherical coordinates. Okay. Okay, so let's see what is our problem statement. If a problem governed by PDE belongs to the spherical symmetry, then the value of m for the solution is given by m is equal to 2. Okay, m is equal to 0 for Cartesian coordinates, m is equal to 1 for cylindrical coordinates, and m is equal to 2 for spherical coordinates. Okay, so our answer will be C, m is equal to 2. Okay, let's move it with the next problem. With the increase in initial concentration, the value of fractional conversion for the first order reaction in a given time. What happens when we increase the initial concentration for the first order reaction is our how our fractional conversion is dependent. So let me write down the equation. I'm sorry, I forgot to bring my laptop pen today. So I will just write it in Excel. Sorry, in Word. So fractional conversion x is given by 1 is equal to x is equal to 1 minus CA by CA 0. Correct? And my if I rewrite this equation, it is in form of CA 0 minus CA divided by sorry, CA 0 by CA. And for first order equation, what can I write? I can write that ln of 0 ln of CA divided by CA 0 is equal to minus of k into t. So I can write that CA divided by CA0 is equal to exponent of minus kt. Correct? So what will be my equation? This one. So I can just write it as 1 minus exponent of minus k into t. So what is the question now? The question says that with the increase in initial concentration, the fractional conversion of first order reaction in a given time, it remains constant because it depends on x is equal to 1 minus exponent of minus k into t. So that's why it remains constant. It does not change when I change the initial concentration. Conversion is not going to get affected with initial concentration. Correct? For first order reaction, not for any other order reaction. Okay. Next question. Consider a spherical porous catalyst. Plots for Ca in the catalyst palette versus distance into the palette are shown. Okay. This is concentration in catalyst palette versus that uh, distance from distance into the palette. So this is r is equal to r radius and r is equal to 0. Okay, they have taken this as R and R. Okay. Which of the plot is most likely corresponding to the case where the reaction rate constant is greater than diffusion coefficient? Okay, so let's assume that reaction is starting from here. So let's say reaction rate is very high. So what is going to happen? Our reactant is easily going to convert in product. So when we move from here to here, so what is going to happen? It's not going to reach from here to here because reaction rate is so fast that before reaching to here, it will convert whole reactants into products. So our correct answer will be option D, where before, I guess these are wrong here. It should be R is equal to 0 and here it should be R is equal to R. So before reaching to the radius, what is going to happen? It is going to complete the reaction. So plot D represents that where reaction rate constant is higher. So let's say if reaction rate constant is very low, so what is going to happen? It is going to take in, it may get some kind of this plot, this or this, depending on the kind of reaction. So it will take time to complete the reaction where reaction rate constant is really low. Okay, so the correct option for this is plot D, where reaction when reaction rate constant is much higher than diffusion coefficient. Okay, let's move ahead with the next problem. Reactions with high activation energy are those temperature insensitive, very temperature sensitive, always irreversible, or always reversible? We really can't say about reversibility or irreversibility of reaction based on activation energy. So option C and D will never be correct one. So it is either temperature insensitive or temperature sensitive. So what happens when activation energy is higher? So what is activation energy? Activation energy is some significant amount of energy that is required to proceed. So what happens? So higher activation energy. So we need higher amount of energy. So what happens when that particular energy is obtained, very high value of energy, we are already at very high energy. So what happens that let's say we are crossing some temperature is X and let's say I'm increasing a bit temperature. So what is going to happen? Activation on energy is already higher. So if temperature is slightest increase, so what is going to happen? Temperature is increasing, meaning collision are going to increase. Collision between molecules are going to increase. Okay. So those reaction will be very temperature sensitive. So correct answer for this is when activation energy is really high, then temperatures are reactions are really temperature sensitive. But let's say it is very low activation energy. So activation energy is very less. So even if I increase the temperature by some amount, it will be not affecting anything. So it will be temperature insensitive when reactions with low activation reaction is with low activation energy. Correct. Okay, let's move it with the next question. The equilibrium constant of chemical reaction dash in the presence of catalyst. So it can either increase or decrease, depends on the type of catalyst, decreases, increasing, or remains unaffected. So the correct answer is remains unaffected. So let me show you some theoretical background for this part. So let me open my 11th spill. Okay, so if we see here, I don't remember the chapter. I guess it is chapter number 9. Okay, here. Okay, so this is effect of temperature on equilibrium conversion. Okay, this is not equilibrium constant. Okay, but from there only we can obtain equilibrium conversion. So see, the thermodynamic equilibrium constant is unaffected by the pressure of the system, by the presence or absence of inerts, or by the kinetics of the reactions, but is only affected by temperature. The second part is, though equilibrium constant is unaffected by the pressure or inerts, the equilibrium concentration of materials and equilibrium conversion of reactants can be influenced. Okay, then Okay, so see here, it is independent of pressure, kinetics of the reaction, and presence or absence of the inerts. So what really catalyst do? Catalyst just alters the rate of reaction. So it is not going to affect our equilibrium constant. So our correct answer will be answer D, remains unaffected when the equilibrium constant of chemical reaction remains unaffected in the presence of a catalyst. I guess these kind of questions are asked in your gate examinations. Let's move ahead. For a first order isothermal chemical reaction in a porous catalyst, the effectiveness factor is zero point 0.3. The effectiveness factor will increase if any of these, what is the effect of catalyst size and what is the effect of catalyst diffusivity. Okay, so what is effectiveness factor? So effectiveness factor is defined by actual rate of reaction for whole pellet divided by the rate evaluated at outer surface conditions. Correct. So when there is a first order reaction, then this eta is given by tan hyperbolic of phi divided by phi. So this phi is nothing but Thiele modulus. So this Thiele modulus is defined by r into square root of k into rho divided by d, that is diffusivity. So the collective effect of diffusivity is when when effectiveness factor is less, and if you want to increase it, so what we need to do, we need to increase either catalyst diffusivity, or we need to reduce the catalyst side. Any of these two will help in increasing the effectiveness factor. So the correct answer will be option D, and this Thiele modulus is defined as surface reaction rate divided by diffusion rate, and that is simplified as R into square root of K into rho divided by D. So the correct answer is catalyst size is reduced or the catalyst diffusivity is increased. Okay. Let's move it with the next statement. The rate of chemical reaction is not affected by the number of molecules of reactants taking part in the reactants concentration, catalyst, and temperature. Temperature is going to affect the rate of reaction, right? Highly going to affect. Temperature, catalyst duty is to increase the rate of reaction, correct? Then reactants concentration is also going to affect the rate of reaction. So our correct answer will be A, where rate of reaction, chemical reaction, is not affected by the number of molecules of reactants taking part in the reaction. Either it depends on concentration. Okay. Okay, so our next question is, which of the following is a function that adds the text description to the data points in the MATLAB plot? Okay, so we know about title. Title, what does title do? Title gives the title to the plot. Whole plot, we can give a title by using title command. Label, we can label the data using label command. Then legend, we can label is meaning X label or Y label. We can give label to axis. Then legend is like, let's say we are having two plots in one graph, let's say there is one x and two y. So to differentiate those two y's, we use legend MATLAB inbuilt function. So the correct answer is text. So when we use this text function, it adds the text description to the data points in a MATLAB plot. Okay, so this was all from last week's lecture. So let's first now understand what is this partial, how to solve these partial differential equations. Okay, so okay, just give me a minute. Okay, so let's learn about pdepe solver to solve partial differential equations. Okay, so the part is before you code the equation, you need to rewrite the equation in this form. So equation is C into del U del T is equal to x raised to minus m del x plus some s. S is constant terms, some constant or some functions of x, t, u. So C is also function of x, t, and u. Okay. So let's say this is our PD. Del u del t is equal to x raised to minus 1 del x of x into del u del x. Okay. So this is, we checked it here when m is equal to, I'm sorry, just a minute. Description part, no, not here. Wait a minute. We just checked that. See here, when m is equal to 1, it solves two-dimensional coordinates. Okay, so this is kind of cylindrical equation, right? 1 by rho del rho rho del f del rho. So this is also kind of cylindrical equation, 1 by x del x x del u del x. So this is cylindrical coordinates. So my m is equal to 1. Okay, now my constant. So here there is nothing multiplied with del u del t. So my constant c is equal to 1. In my function is this del u del x. And my s term, s is something additional term. So here all terms are 0. So my s is equal to 0. Okay. Now let's say I want to solve this PD. This is going to be difficult one. Let's take some easy problem for understanding. Because here they have include those J terms that I don't want to bother right now. Bessel functions. So see this equation. 1 upon x del u del t is equal to u by del x of u by t. So this is my first order equation, right? And this is of Cartesian. So m is equal to 0. Here also you can see there is nothing multiplied of function in del x. So x is m is equal to 0. Then my constant is here c of x t u del u del x. So my constant is 1 upon x. Then my this term function, what is my function? U by t. And what is my s term, additional term? There is nothing additional term. So my s is equal to 0. Okay. So, okay, let's take this problem first. A long cylinder of radius r has a uniform initial temperature Ti throughout. At time t is equal to 0, the cylinder is placed in a medium of temperature T0. The unsteady state temperature distribution inside the cylinder is given by the following partial differential equation. 1 upon alpha del T by del T is equal to 1 upon R del r del t del r. So this is kind of cylindrical equation, cylindrical coordinates. Here r is the radial position, t is the time, capital T is the temperature, and alpha is the thermal diffusivity. Which one of the following gives the correct definition of PDE function for PDE solver? So here, what is the value of m first? My value of m is, if we compare it with here, so what is the value of m? Okay, we need to compare it with this kind of equation. So our PDE is, sorry, where did that go? Yeah, this term. So we can see x raised to minus m del x of x raised to m. So here, what is the what is the coefficient of del r? It is r raised to minus 1. So my m is equal to 1, or anyway we know that this is cylindrical coordinate. So my m is equal to 1. So the first criteria of all these options is we should have m is equal to 1. So we have in option A m is equal to 1, option B is not having m is equal to 1, option C is having m equal to 1, and option D is having m equal to 0. So our correct option is either A or C. Okay, now let's try to define what is value of C. So here value of C was 1. So here what should be the value of C? Value of C should be 1 divided by alpha. Okay. So here C is equal to 1. So this is not the correct option. So we are only left with this. So here C is equal to 1 by alpha. Okay, then what is my function? My function is del T by del R. So correct function f is equal to del T del R. DTDR, that is just a notification. And what is the value of S? S is equal to 0 because there is no additional term present in PD with plus or minus sign. So my S is equal to 0. The correct answer is this. So this is how we can write down our PDE function. Okay, so let's try to do this for this problem. They have given that heat conduction equation. This equation. No, not this one. Wait. Yeah, this one. Let's try to solve this heat conduction equation. Del U del T is equal to del 2U del x square. So let's try to, when we write it in this form, our C is equal to 1. Coefficient of del U del T is 1. Then this term is written right, x raised to 0 del x of x raised to 0 del U del x. So my m is also equal to 0. So my m is equal to 0. C is equal to 1. S is also equal to 0. And my function is del U del x. So let's try to write down the code for this problem. So I will write down first clear all CLC. Then my equation is del U del T equal to del 2U del x square. So okay, let me give a title. Uh, Heat equation, and I will additionally write MATLAB MATLAB documentation MATLAB help document problem. Okay, let's try to solve this. So okay, let's write down the function first. So my m is equal to 0. This first thing we have identified. These values of c and all, we need to define it in a function where I need to write it like this. Function c comma f comma s is equal to name of the function heat pd. Then our inputs are x, mass size, t, time, u, and del u del x. Okay. Okay. So I don't need this. I will just not. I will close this. So I will write down as, I can copy it from here, but I want to show you. So first I will write down function of in bracket c comma f comma f comma s is equal to heat pd. Our input will be x comma t comma u comma function. So what is the function they are defining as du dx? Okay, so I'm just writing it du dx. When I start the function, I need to press one end. Okay, so my c is equal to, what is the coefficient? Okay, let me write down equation here. So my equation is du. I should not write du, but I'm just writing it del u del t is equal to del square u del x square squared. Okay, so my c is equal to here 1. My function f is equal to, I'm just writing it as du dx. And I also need to define s. S is equal to 0. There are no additional terms. So see what is our, okay, let me go there and at the end, or I will have to move from here to there. Okay, so we have defined our function, PDE function. Now I need to use IC function, initial condition function. So what is the initial condition? They are saying that u of x comma 0 is equal to half. What does this mean? Okay, let me first write down the condition. U of x comma 0 is equal to 1 by 2. What does this mean? This means that t is equal to 0 and for all x, my value of u is half. So I need to define this initial condition. So I can define initial condition as function. So what is the output of this? It is u0, my initial condition. So u0, I will write down that function as u0 is equal to, let's say my initial name of this function is heat initial condition, heat I say. And what do I need as input? This format you should not miss. So that is value of x only. X meaning this x we need to define this boundary, not boundary, but length, along the length. So let's say it is x. Okay, I'll put one and. So what is my initial condition? My initial condition is u0 is equal to 0.5. Okay, so really easy. We have defined initial condition. Correct. Now what do I need to do? I need to define boundary condition. Okay, so let me first write down the boundary condition here. I will just write it here, initial condition. Now I will write down boundary condition. Okay, what is boundary condition? U of 0 comma t is equal to 0. U of 0 comma t is equal to 0. And another boundary condition, u of 1 comma t is equal to 1. 1. So this means that when any time when x is equal to 0, my u will always be 0. And for any time when my x is equal to 1 means at the edge, my u also will be equal to 1. So we need to define this boundary value. So how can we do that? So for this, we need to give four inputs. Those are PL, QL, PR, QR, that I will explain you. So let's first write down this. This is really important function. PL, P on left boundary, Q on left boundary, then P on right boundary, or at extreme another end, Q on right boundary is equal to, let's say, heat. BC means boundary condition. And I need to give, I guess, only, okay, value of x, lower x, upper x, we need to give, and corresponding values of u, xl, ul, then xr, ur. This we need to define. And another thing we need to define is time. Okay, time. I will put one end here. Okay, so this term is, so I need to define four values. PL is equal to something, QL is equal to something, PR is equal to something, and QR is equal to something. Okay, so let's check our boundary values. So we can see that all boundary values are single values. It's not like something of derivative. Let's say when u of 0 comma t is equal to minus del t del x, not something like that. It's just simple value. So our both values of q will be 0. When q is only used when there is some first order boundary condition. Let's say it is del t by del x is equal to 0. It is told that when x is equal to 0, del t del x is equal to 0. Those kind of conditions are used for q, but we are not having any those kind of differential equation kind of condition. Those are value equations, so it is denoted by PL and PR. Okay, so on the left boundary, what is that value on the left boundary? It is 0. So I will put PL is equal to 0. And on the right boundary, PL is equal to 0. So I will put as UL. And on the right boundary, it is 1. So I will put as U right minus 1. Okay. So when it is 0, this is, let's say, u left. So u left minus 0, and this is u right. So u right minus 1. U left minus 0 and u r minus 1. So these are our boundary conditions. So till here what we have learned? We have learned this, how to write function. For that we need to know the value of c, f and x. For that we need to convert our equation. Then further we need to we need to write our initial condition and we need to write the boundary conditions. Correct? So this is all about writing our functions. Now let's try to solve this equation. Okay. How solution is given? So what is the syntax for that? This is the syntax. This thing, I'll just copy this. Or let's say my solution is equal to pdepe. Now what do we need? M. Value of M we have already given M, comma, PDE function. So what is the name of our PDE function? Heat PDE. Heat PDE. Then initial condition. So see here also you can see. So initial condition is heat initial condition. Then boundary function. So heat boundary condition. Then Xmass and T-span we need to define. So let's say I am defining my Xmass is equal to, it is 0 to 1. X is equal to 0 to X is equal to 1. So let's say 0 to 0.01. Oh, I'm sorry. Uh, 0 to 0.0121. I'm really taking a very less mesh size. So let's say it is X mesh and my T span. Okay, so T span I need to define. So let's say I'm doing it for some first 30 time interval. So let's say T span is equal to 0 colon 0.1 colon 30. Okay. Okay. So let's run this. Okay. There is some error. On 18th line. This line is showing incorrect. Many. Okay, let's try to understand what is the issue. Okay, it is not here. So let's try to see this problem's solution. So they have written function, all functions. So see, they have defined X value, T value, and M value. Oh, okay, I need to write iterate sign. Okay, I guess this is the issue. Yeah, this is the issue. I need to put iterate sign. Here, okay. Iterate. I guess this is the issue. Yeah, now it is working. It was the issue here. We need to put iterate sign. Okay, so this is my solution. So what were our boundary condition or boundary conditions were? Mm, here. Initial condition when t is equal to 0, when x is equal to 0, my t is equal to 0. Sorry, my x is equal to 0, and for any time my this value is 0, and on the opposite end it is 1. So this is what we are obtaining. Okay, so let's try to plot. Okay, so here we will have to use three-dimensional plot. Let's say I'm plotting a surface plot. Let's say I'm just plotting x versus u. I'm just plotting x versus u. Let's see what we are getting. Yeah, okay, I need to close this. X mess, sorry. Okay, sorry, not you. I guess this is not going to work like this because okay, it is showing the solution, but not like this. I don't want. Okay, so let's go for surface plot. It is a better idea. Surface solution. So see, this is the kind of surface plot that we are getting. It is opening. So this is the kind of plot that we are getting. Okay, so we should also give labels. So let's say label. So X label is my X. Then my Y label is my time. My Z label is my U. U. Correct? Okay, now it will be a better idea. So let's try to see what we can understand, or if we can understand something or not from here. Okay. So when there is time t is equal to 0, my u is equal to, sorry, yeah. Okay, so let's try to see this. See, time t is equal to 0, my u is equal to 0.5 for all these case. See, time t is equal to 0. This is my time t is equal to 0. My u is equal to 0.5. Correct? This one part we have identified. Then one another part. Next condition. Uh, Wait. Let me just close this thing first. Okay. So what is there when my x is equal to 0 for any time? It is 0. For x is equal to 0, I guess this is my x is equal to 0. No, this is not my x. I guess this is what is my x is equal to 0? Wait. Your time is increasing and with that concentration is varying. It is 1 at x is equal to 1. X is equal to 1 for any time it is 1. I guess it is this line. Yeah, x is equal to 1 for any time it is 1, and here x is equal to 0. No, it is not x is equal to 0. Okay, I'm not able to identify this line. It should be this one. No. Okay, I'm not able to identify this line x is equal to 0. This is x is equal to, this one is t is equal to 0. This one is t is equal to 0 line. Yeah, this can't be x is equal to 0. Okay, I guess it is in backside. If I can. Okay, so this is how a surface plot looks like. Yeah, this is time equal to 0 and it is 0.5. Yeah, this is how it is varying. Okay, so this is how we can have a surface plot. If I show just this part. Okay, so this is how we can plot a surface plot. I just want to see one thing, if we can plot one three-dimensional graph or not. So I just want to do plot 3D. Okay, only plot 3. It will be line plot, it will not be a surface plot. So I'm not sure if we are going to get something. Yeah, okay, it's not going to be useful. Okay, so we have to use surface plot SURF. Sir, I'm just trying something. There is nothing like that. Okay. Okay. So we know how to use this surface plot. Yeah, I was just trying something that's not going to be useful. Primitive surface plot. I guess going to understand anything from here. So it is just variation of x with time. So x is equal to 0, 0. Yeah, okay. So these are various kind of things that you can also play and also get something meaningful from here. But this is the surf thing that I taught you, where we can get a surface plot. Okay. So till now, what we have learned how we can solve partial differential equation. For that, first we need to convert our equation into this form. Okay, I have closed that thing. We need to convert our equation in the particular form that we need to give the value of c, our function, and s is s, if it is there or not. Based on that, we need to give these three values. Then we need to define our function u0, initial condition, and boundary condition. Okay, and then we need to solve this. Okay, so let me just save this thing. This is our session 10. here, sorry, this is our session 10, right? Example underscore heat EQ. Okay, so this is saved. So let's try to move ahead with the next problem statement that we are having. Okay, let's try to do it. So problem statement is this one. This is also heat conduction problem. Consider the following problem of unsteady state heat conduction in the x coordinate in the slab of length L, for which the governing PDE is this: rho into Cp is equal to del T by del T, K into del 2x by del x square. Here rho is the density, Cp is specific heat, K is thermal conductivity of the material. The initial and boundary conditions are: value of temperature at any x for T is equal to 0 is 300, and value and at x is equal to 0 minus K del T del x is equal to Q. So here there is not normal Dirichlet condition. This is not Dirichlet condition, and value of T at any L and any temperature is any L and any time is 0. Given L is equal to 0.4, K is equal to 350, rho is equal to 5000, Cp is equal to 1000, Q is 10 raised to 6. At the end of the 10 second, what is the value of T at x is equal to 0.2? Okay, so let's try to solve this problem first. Okay, so here, okay, okay. So what are we given? Let's first note down what are we given. We are given L is equal to 0.4, L is equal to 0.4. Okay, let's do these things at the end. Let's first try to write down the function. So here, the way we did function c comma f comma s. This is not going to change. Equal to, let's say, what can I give the name of the function? PD1. I will just give it as PD1. And what do we need as input? We need our input as x t u del u del x. So here x t, here t and dt dx. Okay. So here we need to first identify what is the value of this C, F, and S. Okay, so here you are having many options. Let's say I'm taking, okay, let me close this file also. It's not required as of now. Not also this one also. Let's say I just consider equation in this form. So my value of C constant will be rho into Cp. So let's say I'm writing it as into Cp. So for that I need to define rho here. So my rho is equal to, what is the value of rho that is given to us? What is the value of rho that is given to us? That is 5000. And value of Cp is given to us as, let's have a habit of writing units of kg per kilogram per meter cube. That is the unit of density. Now specific heat Cp is given as 1000 joules per kg per Kelvin. Not 1000, sorry, 100. This is 100 joules per kg Kelvin. This is the value of Cp. Okay, so I have defined C. Then I need to write my function. Function is K into dt dx. Correct? My function is equal to K into dt dx. So I need to define what is K. So value of K, that is thermal conductivity, is given as, sorry, value of thermal conductivity is given as, where is that value? Yeah, 350 watt per meter per Kelvin. Okay. So the value is 350. That unit is watt per meter into Kelvin. Okay, so I have defined my function. So what we can first do, and what is the value of as there is no additional term with plus minus, so it is 0. Okay, so here what we can additionally what we can do to differentiate this problem here, there is one more option. We can also take C as 1 and our equation is K divided by rho Cp, or we can also take C is equal to rho into Cp by K and equation is just dt dx. That is up to you how you want to define it. Okay, so this is the value of, this is the function for partial differential equation. Okay, now what do we need? Okay, let me do one thing. Let me write down my equation here the way I did it here. This one is, I guess, problem number 6. 6. Okay, and my equation is rho into Cp into del T by del T is equal to K into del square T by del X square. This is my equation. Okay. And what are the initial condition? Let's try that. U at T is equal to 0. T at T is equal to 0 is 300. T at T is equal to 0 is 300. 300. Okay. Now second boundary condition. Boundary conditions. So here there is a catch in boundary condition. So at X is equal to 0. So my boundary condition T 0T is minus K into dt dx is equal to Q. Okay, this is my one condition. Okay, and what is my second condition? T at L comma T. It is 0. Okay, so this is my equation. Okay, so I need to now write down my uh, initial condition. So let's say for initial condition, let's first see the syntax. So the syntax is function T0. T0, I'm just maintaining it uniform for better understanding. T0 is equal to PDE, sorry, PDE initial condition of, I just need the value of X. Correct? And that initial condition T0 is equal to 300. Okay, that we have given T0 is equal to 300. Okay, now we need to define our boundaries. So function, what do we need here? Here we need so many things. Function. What is that? PL, QL, PR, QR. Correct? That is equal to, let's say, PDE, boundary condition. And for that we need to give XL, TL, XR, TR, and time. Similar to this, XL, UL, XR, UR, T. Here it is our variable is temperature. So XL, TL, XL, TR, T we need to give. Okay, so we need to define now PL is equal to something, QL is equal to something, PR is equal to something, QR is equal to something. Okay, so let's first go towards right boundary. So for right boundary, it is just UR minus 0. And there is no differential equation term, right? So it is just UR minus 0. So I'm just writing it as, sorry, not UR, TR. TR minus 0. And this QR is equal to 0. Okay. Now here, there is no Dirichlet condition, right? Here, this side. So it is 0. And this term, what is this condition? Minus K divided by Q dt dx is equal to 0. Correct? How can I write it? I can write it back as minus K divided by Q dt dx is equal to 0. So what will be this value? My QL will be minus K divided by Q. Okay, so minus K divided by Q. So here also we need to define what is K and what is Q. So value of K is equal to this thing, same we need to copy. Value of K is 350 watts per meter Kelvin. Kelvin. And what is the value of Q? Value of my Q is equal to, what is it given in the question? 10 raised to 6 watt per meter square Kelvin. So let's say it is 10 raised to 6. So I can write it as 1e 6. And that unit is watt per, what is the unit? Watt per meter square. Watt per meter square. Okay, so we have also defined our boundary conditions, initial conditions, and function. So let's move ahead with our calculations. So we need to define X mass. This thing we need to define. So here also my M is equal to 0. Then I need to define X mass. X mass is equal to, let's say, 0 to, what is our length? In question, our length is 0.4. So 0 to 0.4. So let's say I'm going in interval of 0.01. Okay. And T span, time is not told to us or told to say, it is told to us 10 seconds. 10 seconds is told to us. So let's say 0 to 10 in interval of 0.01. It's not told to us exactly 10 seconds. We are supposed to find the value at 10 seconds and at x is equal to 0.2. Yes, we need to go with 0.02. Then only we'll get 0.2. Okay, so this is the thing. So let's say our solution solve is equal to PDE, PE. I need to write first M, then I need to write my PD function at the rate PDE fun, then initial condition at the rate PDE, initial condition, then at the rate PDE, boundary condition, then my X mass and my T span. Okay, so let's try to run this. Okay, so we have run it. So if we see here, Okay, so we have this thing with us. Okay, so this is my last t is equal to, yeah, this is my solution. We have total 21 x mass. So this is my solution, and for 11th, when x is equal to zero point 0.2, so this 11th, what is the value? 272 point something. So from option it matches with 275. Okay. So correct answer is 275. If I further reduce it 0.0 for better accuracy 0.002, then we have increased our x mass. Okay. So what is when zero point 0.2 is, we are not getting, yeah, we are getting at 101, it is zero point 0.2. So if we go to solution at 101 time, 101, and at last time, that is this one, really at the end, yeah, so it is 272.69. It's not affecting actually. So further what we can do, it is 1014 for x. So what further we can do, we can even reduce this time, but I guess it's not going to affect. It's not going to affect anything. It is same 272. So now what we can do, I can plot my solution for just last time interval. Sorry. Yeah, so only for last time interval. So how is it varying? So I can write that, let's say t underscore 10, 10s, I'm writing 10s is equal to sol. What is that? This thing. Last row and all columns. So I will write last row, that is end row, and all columns. So this is my t, and I can plot is as plot. On x-axis it is x mass, and on y-axis it is t underscore 10 second. I can give some x label as x, y label as t equal to 10 second, t underscore 10 second, not t is equal to 10 second. Okay, so let's try to plot and see what we are getting. So this is something we are getting. Okay. So, okay, this is one thing. I also want to plot on surface plot. So I will do surf x mass, comma t span, comma solution. And these things, x label, y label, and z label, t, and z label is t. Okay, let's try to plot this. Wait, it let it's still loading. Yeah, it's taking some time because our x mass and those values are really, really, really small. Yeah, it is still running. Just wait for some minutes. I just want to see how this surface plot looks like. taking really, really long time. It's not opening, so let's. I don't think if this is also going to work now. We'll have to wait. Okay, let's keep it. Let's leave it here as it is for some time. After some time, I will get back here. So let me save this problem statement. Let me save this problem. Assignment 9, problem 6. It is not even saving it. Mhm. We'll have to wait for a minute. It's not working. Okay, let's get back to here after some time. So from this problem, what we have learned to we have learned how to use pdepe in build solver. For that, we need pde function. We need PD initial condition function. We need PD boundary condition function. Even we need value of M that is equal to 0 for one dimensional or Cartesian coordinates. M is equal to 1 for cylindrical coordinates and M is equal to 2 for spherical coordinates. Oh, this is not working, man. Okay, let's move ahead. Okay, so let's take one more problem to solve this partial differential equation. Okay, not this one. Okay, so this problem, in this week, we will learn to use MATLAB functions for solving partial differential equations. The case that we consider is that of a parabolic partial differential equation in one spatial dimension. Consider a one-dimensional channel experiencing diffusion with the concentration of the species governed by the equation given below. Del C del D is equal to K del square C del X square. Where the diffusivity of the species in the medium has been denoted as D. The initial condition is C at x, and any x and t is equal to 0 is sine x. The boundary conditions are C at x is equal to 0 anytime t is 0, and C at x is equal to L anytime t is 1 millimoles per centimeter cube. Here we will have to be careful with units. The length of the channel is 25 centimeter. For the system with the specifications given above, determine the evaluation of concentration in the channel considering diffusivity as 0.15 centimeter square per second. Let's do one thing, as this is our concentration problem and concentration can't be negative. Sorry, it's not working. Guess I have not stopped sharing it. Yeah, it is sad. Yeah, because of this, it's hanging. Okay, so here what is the issue? It is sin x term. So sin, it is positive, negative, positive. So let's do one thing. Let's take sin x plus 1. So everything is positive only. Okay. So we have taken our initial condition as sin x comma 1. Okay, so let's try to solve this problem. Okay, let me close this. Yeah, I want to save this. Let me just close this, or else our laptop will be slow. Because of this mess size, I should not have done this with really small mess. It's not now even opening that window. This is really difficult. It's not working, guys. Okay, let me do one thing. Let me open one more MATLAB. Yeah, okay. This is the thing that I need. Okay, let me just save it. Live sessions, this thing, assignment 10. Okay, I have saved my problem. Okay, so I can happily close that. Okay, so let's try to formulate this problem. And I don't need this additional MATLAB now. So let me just close this one. Okay, so our equation is, what is that equation? This fixed equation, right? Okay, let me write down fixed equation. Okay, what is that equation? Del C del T is equal to K into del square C by del X square. Correct? And my value of C at T is equal to 0, NaX is sin X plus 1. We have taken intentionally plus 1 just to keep our concentration positive. Sin of X plus 1. Concentration at NEX, 4x is equal to 0 and NET, it is 0 and another term is 1. Okay, here it is 0 and here L is 1. Okay, so let's first try to write down the function. So I will write function. Okay, what is the value of M? Here also value of M is equal to 0. Okay, so first let's try to write down the function. So my function is function. What do we need? We need function C comma F comma S. C comma F comma S is equal to pde function pde function that is x comma t comma c comma dc dx. Okay, and so c is equal to, what is the value of c? Here there is no coefficient of del c del t term, or I can take 1 by k, but let's keep c is equal to 1. C is equal to 1. Okay. Okay, wait, let me just check the equation. My equation is del C by del T is equal to, okay, here it's not K, here it's D. I'm sorry. D del square D del X square. Here it is D. So C is equal to 1, correct? Then my function F is equal to D into dc dx, correct? And my S is equal to 0. Okay, I hope this term is clear to everyone. So here we need to define the value of D. So my value of D, what is the value of D given in problem? Value of D is given to us as 0.4 problem 1.15 centimeter square per second. It is 0.15 centimeter square per second. That is the value of, okay. Centimeter square plus second, I need to put it in comment. Centimeter square per second. Correct. So this function is done. Now next function for initial guess. So function, let's say C0 is equal to PDE initial condition. So I'm writing it as PDE IC. And for that I need the value of X. So I will put and here. So what is the initial condition? C0 is equal to sine of X plus 1. Really weird initial condition, but this is what it is. Sine of X plus 1. Okay, now we need to define our boundary condition, correct? So our boundary condition function, what do we need here? P left side, Q left boundary, P right boundary, Q right boundary. That is equal to PD boundary condition, and that function is of X, what is that function of XL, UL, XL, CL, XAR, CR, and T. Okay. So that is of XR, XL, CL, yes, XL, CL, then XR, comma, CR, comma, time. And now what do we need to define? We need to define all these value of PL is equal to something, Q left is equal to something, PR is equal to something, QR is equal to something. Okay. So what is the value of P? Okay, let's see one thing. Are there any boundary condition of DC dx type? No, there are no. So both this QL and QR term will be 0. Okay. Now what is the value of PL? Value of PL is CL minus 0. So I will just write it as CL. And value of PR, what is the value of PR? Value of PR is CR minus 1. So I will write it as CR minus 1. Okay, so our problem is ready. So now what do we need to do? We need to write down X mass is equal to 0 to, okay, what is the length given to us in the problem? Length given to us in the problem is 25 centimeter. So 0 to 25, let's say I'm going in the interval of 0.1. Okay. Time is given to us. No time is given to us. Okay. So let's say I'm going it for T span is equal to 0 to 30 in span of 0.1. I'm just putting some random values. Okay. So what will be my solution? My solution will be equal to, what is my solution? Solution is equal to my MATLAB inbuilt function pdepe, then in bracket first value of m, then my function at the rate pde function, then at the rate pde initial condition, then at the rate pde boundary condition, correct? Then x mass and then t span. Okay, so this is my solution. Let's say I want to plot my solution for last t is equal to 10. Okay, so c underscore 10 second, sorry, 30 second is equal to, what will it be? It will be solution last row and all columns, correct? And if I plot this, plot x-axis x mass and y-axis c underscore 30s, then my x label will be x and my y label will be concentration. Okay. Okay. So let's try to plot this and see what we are getting. Okay, I'm sorry, I need to wait. Let me replot it. Hmm. So concentration is increasing with time and it is getting constant. Wait, guys, let me just save this thing first. Else if something hangs, it will be difficult. Okay. So this is how it is varying. It is getting constant. Let's say I am doing it for more. Uh, let's say I'm doing it for total 60 seconds. So I will call it as 60. So see, it is showing a better result after 60 seconds. Correct. So this is how my concentration is reaching 1. and my diffusivity is 0.5. So when are we getting steady state after some 60 seconds? Let me try it for 50 seconds. So 50 also we can see what we are getting. For 50 also it is steady state. 445, 440 it was not a steady state. Let's see 445. Yeah, 445 also it is more or less steady state, but 440 it was not. It was still fluctuating. Okay, so let's just do it for 50. So we have shown this plot how concentration is varying with x. So what we can further, so we can let's plot one surface plot. Surface x mass, comma t span, comma solution. Then x label is my x, and y label is my time, and my z label is my concentration. So surface plot, how it looks like, let's see. It will be a bit messier. So if I open it, it's not. Yeah, okay, it will happen. So if one thing you can see that at initial time C, it is a sinusoidal wave. Okay, it is not opening it in new tab. I don't know why. Okay, wait. We have to wait. I'm doing it really slowly. Yeah, there are many plots open. Let me close one more. Yeah. So see, we can see that at time t is equal to 0, this is this sinusoidal wave. This thing, this inner part is, I guess, time t is equal to 0. No, this is also time t is equal to 0. Okay, so this is how it looks, correct? With x, with time, and with concentration. So now let's move it with the next problem statement. I'll just keep this in comment. I don't want to plot surface plot because it is really difficult to wait. Now, what is my next question? Determine the equilibrium concentration profile in the channel. So we have already determined the equilibrium concentration profile, and we checked it at some t is equal to 50 seconds. It was in equilibrium. Okay. So next question is determine the effect of diffusivity on concentration evaluation by reducing and increasing its order by value by order of 2 magnitudes. Okay. So let's say my first value of diffusivity, let's first reduce it by further 2 orders. So it will be 0.0015. So 0.0015 first order. First, let's reduce it. So I'm reducing it by uh, 2 orders. So see, when I reduce it to 2 orders, I'm not getting steady state within 50 seconds. Okay, this is what we are observing. And when I increase it to 15, so it is following some linear trend. Okay, I should not use word steady state. I should say that that variation with x is linear. Okay, so this is how effect of diffusivity is. And our last statement is verify whether your result depends upon the resolution of space grids and time. Okay, so let's do it for, let's first see what is 0.15. So 0.15, I am getting this kind of curve. So let's say I am increasing my grid size from 0.1 to 4x mass, it is 1. And for time span, let's say it is 2. So are these results affecting? Okay, here it's not visible. See, results are getting affected with grid size. See, results are getting affected with grid size. So this is our conclusion. Okay. So this is how we can solve partial differential equation. So what we learned here is, first we learned how we can this is how we can learn partial differential equation, solution of partial differential equation using pdepe MATLAB inbuilt function. So using pdepe MATLAB inbuilt function, what do we need to give? We need to give the value of m. M is equal to 0 for Cartesian coordinates, m is equal to 1 for cylindrical coordinates, and m is equal to 2 for spherical coordinates. Then I need to define my PDE function. So for that we need the value of c, that is the coefficient of del c del t term, then value of function, and value of s, that is some additional plus minus term. Then we need to define our initial condition, then final condition, boundary condition. So for boundary condition we need PL, QL, PR, QR. So value at leftmost boundaries and rightmost boundaries. We take value of, we take P when it is Dirichlet boundary condition, and when we take Q when it is Newman boundary condition. Okay, so this is what we have learned using PDE MATLAB inbuilt function. There is one more thing that we will learn, but not for today's class, for next week. So that is PDE toolbox. So let's first take some assignment question, and then let's, if time permits, we will just see basics of PDE toolbox. Okay, the first question is the PDE toolbox in MATLAB uses which dash for the solution of several types of PDEs. Okay, so let's go to MATLAB help box and see PDE toolbox. PDE toolbox. This one. There are various examples available here. Various names in various versions. Okay, there are various examples available. I need some theory part, but I am not able to find it right now. So let me put back. Okay, somewhere there should be some theory about PDE toolbox. They are not saying anything. Okay, but the correct answer is PDE toolbox that we are going to learn that uses uh, finite element method. Let me check it. That uses finite element method. So let's try to just understand What is finite element method? So finite element method versus finite difference method. Okay, so if we read this, finite difference method is used in computational fluid dynamics course to solve complex problem. Wait. Okay, so see here in finite difference method, it consists in replacing the derivatives by finite differences with some modifications. Let's say d square y by, it is dy by dx. So we write y I plus 1 minus y I divided by x I plus 1 minus x I, like that. But in finite element method, it uses a variation formulation in a way that automatically accommodates the boundary conditions. Okay, so the correct answer is finite element method. Oh wait, let me save this problem. Okay, it is saved now. Um, it is saved. So the correct answer is finite element method. Okay, let's move ahead. In the draw mode of PDE toolbox, the combination of solid objects is done by formula of set algebra plus minus. Okay, let's see this PDE toolbox. Let me give you very brief idea. So we need to go to app. If it's not available, then you need to install it, PDE modeler. I was not having it earlier, so I had to install it. So it will take some time to open it. Yeah. So this is our PDE modeler. So see here, we can draw our object. Let's say I have something circle. So I can draw it circle. Correct? Then when I click on this, I can give the value of, let's say my center is at 0 and my 0, 0 is my center, and let's say my radius is 1. I can also do this. Okay. So this is my PDE. This is my problem. Okay. Then what I can further do, I can define boundaries. So I can go to boundary mode. So there is only one boundary. It is taking time to open. Not this thing. I can convert my problem into this kind of various problem, diffusion problem, heat transfer problem. Let's try to do it in diffusion problem. I don't know if it's going to work or not. We will take these examples of heat transfer next week. Yeah, it is opening this thing only. I need boundary conditions, so that is not coming up. Okay, then if we go to PDE mode, we can define our whether it is an elliptic PDE or parabolic PDE. Correct. These also we can define. I will again go to this boundary part. Okay, yeah, specify boundary condition. I need to click on specify boundary condition. So see, I can also give whether it is Newman or Dirichlet boundary condition. These I can directly provide from here. Then when I solve this problem, let's say I'm just this is something random problem. It is not a physical problem. So see, this kind of mess is created by using mesh. I can also refine my mesh. Okay, I can again refine it. So this is how we can, if I jiggle mesh, so see, you can see the difference. I can even refine the mesh. So you can do this now. If I solve this PDE, I just have to click on solve the PDE. So see, we can see this kind of profile. So see here, profile is in based of color. When the lightest color is 0 and the largest color or darkest color is indicating highest value. Okay, we can do many things. Let's say if we go to boundary condition, specify boundary condition. If we change this weight function from 20, we can see the effect. And let's say it is Newman boundary condition and Q is equal to some 10. That also, I'm just doing some random stuff. It may not physically make any sense. Okay, there are no significant differences actually here. Okay, but what we can do even here, let's say my sign initialize mass. So let's say if I am plotting with this kind of mass where it is coarse grain, not fine. So there also we can see the of effect on the solution. Currently it's not way visible, but when we will deal with actual physical problem, we will be able to see how these small values are going to affect our solutions. So this is how PDE works. Okay, so there are, when we go to draw mode, uh, how can I delete this? Okay, let me close this and let's take this problem and see what we are getting. So I will again open this PDE modeler. Okay, so see there is some plus sign. I can specify my object like this. Okay, like this I can do. I can specify my second boundary. Like this I can play with my parameters. Let's say it is something irregular shape, something like this. So this also I can do. Okay, so this is how we can define our object. Then after defining object, we need to keep on boundary mode, and then boundary mode is enabled. Then I need to click on this boundary and I can specify the values of boundary condition at this particular boundary. So this is how we can do this. So the question is, in the draw mode of PD toolbox, combination of solid objects is done by the formula of set algebra, say plus minus and multiplication. So this is correct. This is how we can also do it. Then this third question, for the values of x and y, what values of x and y, the PD will be elliptic PD. Okay. So for the PD to be elliptic, my b square minus AC should be less than 0. Okay, so let me go to what I am not having my sketch pen right now. Okay, so my when I compare my PD to our standard formula, so my value of A will be equal to 1 plus y. Then my value of B will be equal to minus of 1 minus x, because in equation there is already 2. So minus of 1 minus x, correct? And my value of C will be equal to minus of 1 minus y. 1 minus y. Okay. So for my elliptic PDE, what is my condition? My condition is, okay, my elliptic PD, what is my condition? B square minus B square minus AC is less than 0. So B square is my minus of 1 minus x whole square. So it will be 1 minus x whole square minus a into c. So it will be minus minus plus plus 1 plus y, 1 minus y. So that is 1 plus y into 1 minus y is less than 0. So my equation is 1 minus x whole square. Okay, let me copy this. So it is 1 minus x whole square into 1 plus y. 1 minus y is 1 minus y square. Okay, so it is 1 minus 1 minus y square. this should be equal to 0. So let's see what are the options we have. If I put x is equal to 0, y is equal to 1, x is equal to 0, and y is equal to 1. So my answer will be 1, and 1 is not less than equal to 0. So A is not correct option. Let's say x is equal to 1, y is equal to 0. X is equal to 1, this term is 0, y is equal to 0. So that also gives 1. So this is also not my solution. Then x is equal to 2, y is equal to 1. So my x is equal to 2. My this term is 1 minus 2 whole square, that is 1, plus my y is equal to 1. So 1 minus 1 0. So that is also again 1. So that is also not a solution. My last option is x is equal to 1, y is equal to so if I put x is equal to 1, so 1 minus 1 whole square. So this is 0, and y is equal to 2. So 1 minus 2 square. So 1 minus 4 is minus 3 is less than equal to less than 0. So this is my correct option. That value of x is equal to 1 and y equal to 2 will give me elliptic partial differential equation. Okay, let's say I want to check for hyperbolic. So for hyperbolic, what is the condition? Hyperbolic PD, my b square minus AC is greater than 0. So for hyperbolic PD, this is my condition. B square minus AC is greater than 0. Okay, so this whole term should be greater than 0. So if you remember, our all options 1, 2, and 3 were giving us value of x greater than value of this b square minus ac greater than 0. And let's say if I want parabolic PD. So for parabolic partial differential equation, what is the condition? Our condition is this: b square minus ac is equal to 0. So what can I put? I can put, if I put x is equal to 1, y is equal to 1, it will be 0. If I put x is equal to 1 and y is equal to minus 1, that is also 0. So similarly, you can find so many solutions. Let's say if I am putting x is equal to 2. So my this term is 1. And even x is equal to 2 and y is equal to 1 is a solution. So there are various solutions depending upon our x and y conditions. Okay. So let's stop here, and we will see again. We will meet again next week. So let's revise what what we did today. So today we looked at partial differential equation. First, we started with various kinds of partial differential equations. So those were, okay, I have noted them down. So those were elliptic partial differential equation, then hyperbolic and parabolic partial differential equation. So for elliptic partial differential equation, or all eigenvalues should be of same sign. For hyperbolic PD, there are some positive, some negative. And for parabolic PD, at least one eigenvalue should be 0. After that, we used pdepe, MATLAB inbuilt function. And for that, we took some three problems. We take m equal to 0 when we are dealing with one-dimensional Cartesian coordinates. Then we take m is equal to 1 when we are dealing with cylindrical coordinates. We take m is equal to 2 when we are dealing with spherical coordinates. Then further what we do, we further solve three problems. For that we use pdepe, MATLAB inbuilt function. So for that, what do we need? We need to define our first one, we need to define our value of c, f, and x. So what is c? C is the coefficient of dc dt, or time variation term constant. So for most of our problem, value of c was equal to 1, or it can depend. That we did. Further, f is our function and s is equal to some addition in differential equation. So those terms were 0 in our case. Then we use PDIC, that is initial condition function. Using that, we give initial condition, and for boundary condition we have PL, QL, PR, QR. So P is Dirichlet boundary condition, that let's say u at x comma u at 0 comma t is equal to 300. That kind of condition is used in PL. And QL is, let's say I'm having minus k dt dx is equal to q. So that kind of condition is called is used in QL term. So using these three function term, initial condition, boundary condition, we solved partial differential equation using pdepe tool, where we need m pdepe function, initial condition, boundary condition, xmax and tspan. Further, we also learned today how to plot a surface plot, and from that we estimated how concentration is varying with particular time, how concentration is varying, and how its variation is with d diffusivity. We also checked what is the impact of x mass, or the size of mass that we are taking. Then further we started a very little part on PDE toolbox. This we are going to learn next week, where we are going to solve these two main problems of heat conduction problems. This we are going to solve using PDE toolbox. So this is all for today's class from my side. Yeah, this is all for today's class from my side. If you are having any query or anything you want to ask related to this MATLAB course, please feel free to write me an email. Sorry. Yeah, please feel free to write me an email on this particular email ID. I will try to resolve your query as early as possible. So thank you so much, everyone. We will meet on next week. Okay.